Now that we have installed Visual Studio Code and Platform IO, we are ready to do an application. Let me create a new project and let us call it a generic project because it is general in nature and it can be considered as a template so that you can use it for other applications as well with modifications. So let us go through the process of how we would develop as a systematic way of developing the code. Again, the objective here is not on code development. The objective here is on the process that we follow, and it should be valid for any microcontroller, except that the syntax will be different for different microcontrollers. But the general process will still remain the same. So let me go to home. I'll go to home here, right? And go to projects. And let me create a new project. So I can go here, create, click on that, give a project name, and let me give it as generic. This generic project, and I am going to select from ATtiny, 85, so that you have this generic ATtiny 85. Click on that, and I will like to have a location. So let me first open a folder. So let me go into the AVR folder, and within that ATtiny. So in that ATtiny, I would like to create the we have the blink as the example that we saw while installing the Visual Studio Code and Platform IO. Here will be another called generic that will pop up. Okay. So let me go here and choose the directory, the same directory which I wanted. Let me go to AVR, and within this ATtiny, I will say finish. Okay. So now that it is created, you see this generic is created. I can kind of make the blink smaller, and you see that generic is now showing up here. And if I go to Platform IO, see environment is ATtiny, Platform, Atmel, AVR, and I will also give the upload protocol. So in the Blink Platform IO, we had this upload protocol as USB ASP. I will copy it and paste it there so that I will use the same upload protocol, same USB ASP. Okay, then we save it and move ahead. So in the source, there is main.cpp. So it would have created a kind of a template. Okay. So I don't want this. Let us create from scratch. So let me first define CPU clock frequency, and I will say that if not defined, f CPU, I shall define f CPU as a 8 megahertz, clock. So I will comment there and say clock frequency of 8 megahertz. So keep commenting as you go. It is helpful. And I'll say end if. So this completes the directive, compiler directive. Okay, next, include. Let me include. I will include avr io.h. Then I will include, now this is important, interrupt. AVR's interrupt. It has all the interrupt vector definitions .h, and also include any other packages that you need. Right now I will not put anything. I'll just leave it at these two. Okay. So the includes will come at this point, all the includes. So if you are going to use the delay, you can use the util delay.h at this point. But I'm not going to use the delay routine right now, so I will leave it at that. Now, important, which normally people will fail to do, is set up the interrupt vector table. See, most of the programs you will use interrupts and you will have ISR routines. So I will set up the interrupt vector table, and this is something that you should not miss. Whichever the application, have the interrupt vector table set up. Interrupt vector table. Okay. So what is the interrupt vector table? So if you go to the data sheet, of the Atmels AT Tiny 85, okay. So you kind of move down. Let me go down to where I can see the interrupt. It is pretty down. Let me scroll down. So here it is, section 9.1, interrupt vectors in AT Tiny 25, 45 and 85. This is the table. So it gives the vector number and the address. What is the source of the interrupt? Reset, external interrupt, and the definition. Okay. So you need to have a ISR opened for each of these, except the reset, each of these, and close it by having a return, or in the assembly giving a no operation, so that if there are any spurious interrupts happening, it will not just go and hang at some point until you go and press the reset, where the program counter will go back again to the main program. You need to have an exit from every ISR. So you need to consciously do this, and all the ISRs should be properly software terminated. So let us do that. It's a very important step, and should be done in every. It should be done in every application. So remember this, or you take a snapshot of it, and I will use these exact source names, and to that I will append in the end _VECT vect, and that, because that is how it is defined in the interrupt .h for the vector address, so that you know where the ISR has to go on the occurrence of this particular interrupt. So take a snapshot of this, or you download the datasheet, keep it by your side, and I'm going to go in this specific order. Okay. So let me go back to the code and start setting up the ISR. So I will say ISR, and the first one was int 0. That was the source name, underscore, I'll give vect, and close the parenthesis. So this is the int 0 ISR, and within that will be the code. So the code here is nothing but just return. So all I'm going to just use this. Within the braces, it is just return. Okay. And after that, I will give a comment saying that this is an external interrupt request. Okay. So that this will take care of any spurious request that will come to int 0, and it will have an exit path, it will return and then come back. So like that, let me create for every interrupt. Let me do that. So you can see that there are 15 interrupt sources. If you leave out the reset, you need to have the ISR for 14 interrupt sources. So let me go back to the program and let me the next interrupt which I am writing here, ISR PCINT0 underscore vect. This is a pin change interrupt request. Then after that, ISR timer 1 compare A vector. Timer counter 1 compare match A. Then you have timer 1 overflow. So timer counter 1 overflow interrupt. So ISR timer 0 overflow interrupt. And you have the EEPROM ready interrupt. Or this returned twice. The ISR analog comparator underscore vect. ADC conversion complete. Timer 1 compare B register match. Timer 0 compare A vector. Timer 0 compare B. The USI start universal serial interface overflow. So these are the vectors, right? So this is duplicate. I will just remove that. Okay. So all these are terminated with return, which means that any given point in time during the operation of the microcontroller, if there is any spurious interrupt, this will go through, exit out, and then come back again to the main program. Now, I may want to use the timer 0 overflow. So let us say I want to use the timer 0 overflow. So I will take that. So timer 0 overflow, what I will do is that I will open it out, return, and I will close it in this fashion. So this timer 0 overflow, I can use it to put in some code when there is a timer counter 0 overflow whenever it hits the bottom. Whenever the counter hits the bottom, interrupt is generated by the timer 0. It will come to this location and execute this code here. Okay, so I can later on put some code in there. So right now keep it there because I want to do a PWM and I will show you how to do that. So next, so I will now come to the int main void. So this is the main code, right? So there are a lot of things that I need to do, and I need to initialize. If you are having several events, so the event managers, like the I may use a ADC, I may use a PWM. So I have to initialize these event blocks with some control words, so that so that it will behave according to some particular manner as given in the data sheet. Then after I do the initialization, which means that I will have some initialization statements, then I will have the while loop. So this is the infinite while loop, which the microprocessor will do. And after that, this is optional in some of the compilers, return 0. That is a good practice to have that. So this will be the complete thing. So there are some parts of the codes that you need to fill, that is initialization part, and here the ISR part. So let us do that. Let me save this in the meantime. Save. So let us now come to this part, initialization. So let me initialize timers. So I will choose one timer called the timer 0. It contains two compare registers A and B, and can be used for PWM generation. So let me initialize this. So you need to have your data sheet by the side, so that you can actually look at the control words. What are the control words that you need to use in order to manage the timers? So the timer 0 is managed by two control registers, TCCROA and OP. And then we will try to see what are the control words that we need to put into these registers. So let us go to the data sheet. So in the data sheet, move to the section on timers. So here it is. Here is the section on timers, 8-bit timer counter 0 with PWM. So you can read through all this. I am going to just show the block diagram here. You see that there are two pin connections, contacts, output connects, OCNA or OC0A. N is for timer 1, N is 1, timer 0, N is 0. So OC0A and OC0B, these are the ones which are actually connected to the pins of the microcontroller, and they can be enabled or disabled. So if you go back and look at the pins of the microcontroller, you see that here this is the some of the pins have multiple functions. Now look at this OC0A. So this is the timer output, the timer event block output. So this is available at PB0. At PB1 you are having OC0B, timer 0's second output. Let us see how we can manage these PWM ports and what are the control words that we need to give. So let us go back to that timer counter register. So here there are two registers, TCCROA 0A, TCCR 0B. These two registers are the ones which kind of manage the way these timers behave, and these are the ones which you need to initialize. So what are the values that we need to give to these two registers? So let us look at kind of a deeper deeper cutaway part of this TCCR 0A and 0B. The cutaway part of the timer register is like this. So you see that here are the 8 bits, and let me highlight them for you. So these two are for compare match output of the A compare. So it contains 2 bits, and then 2 more bits are for the B compare match output. These two, I will take a different color. So these two are for the B output, and this last 2 bits, the bits number 2 and 3 are reserved. The last 2 bits are for waveform generation, which actually will come to the output pins OC-OA and OC-OB. The waveform generation, actually, do you want sawtooth, do you want up-down counter, that kind of things will be, it will be based on that, and based on that, the output to the pins will automatically or accordingly be given. So if we look at this, so let me go down. So here you see for the compare outputs, what does it mean? Look at this table. So you have to look at the data sheet. If I'm having 0 and 0, it means both OC0A and OC0B are disconnected. So if you don't want to use them as PWM port, just give 0, 0. That's it. It will not be connected. So no PWM will come to the pin PB0 and PB1. So 0, 1, if you give it as this, then OC0A and OC0B on compare match, that will toggle, and 1, 0 means clear OC0A and OC0B on compare match, and 1, 1 means set OC0A and OC0B on compare match. Okay, so we will take this, which means, let me mark this one as, initially everything, the values are set as 0, 0, 0, 0, initial values. So I would like to have this as 1, 0. I will use only one PWM port, OC0, OC0A, and I will keep this one as 0, 0. So this anyway are reserved words 0, 0, and waveform generation. Let us see what the waveform generation means. So when we come to the waveform generation mode, see it has 2 bits in the TCCR0A register and 1 bit, WGM02 bit in TCCR0B register. So let us say we have these 3 bits. So 0, 0, 0 means normal. 0, 0, 1 is PWM phase correct operation. 1, 0 is CTC, 1, 1 is fast PWM, so on, right? So let us choose this fast PWM, 1, 1. We need to get 1, 1. So if I go back to the control word, so I have to make this 1, 1. So this is the control word I have to give for TCC R0A. So let us write that down. So remember this control word, or you can kind of put it as a comment in your code. Let me do that. Let me open this. So let me first initialize TCC R0A is of the form. I know this is only a comment, so I will just make it a comment so that you remember what it means. So you saw that first it was COM0A compare A1, compare output 0 A0, then compare output B1, compare output B0, then it was reserved, then another reserved, then you had WGM01, WG waveform generation mode 0, 0. So these were the bits. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay. And I could set TCC ROA. TCC ROA is equal to 0B. Okay, I can do that and then give it as, what did we say we wanted to give? This fraction. We wanted to give it as 1, 0, 0, 0. This is always 0 and 1, 1. Okay, so we type in that. 1, 0, 0, 0, 0, 0, 1, 1. So this would be the control word that you want to set. But one thing is that binary not all compilers recognize. So you may have a problem with some compilers. Hex and decimal, of course, the compilers take in. So you can give this. It is, and if you are having datasheet by the side, this is a very compact way of defining the control word. But the recommended way with different microcontrollers, the positions of these bit variables can change. So it may not be compatible across different microcontrollers, even of the same family. So therefore, what is recommended is to use the variables, the bit variables. So I will make this as a comment and then say, okay, this is what I want to set. I want to set this, I want to set this, and so let me write that down. TCC R0A. With itself I will R equals. So I want to set WGM01 and I will R also WGM00, and I also would like to set compare output A1, right? So I will R COM compare output A1. So you are setting that. So these will get set. You can leave it at that. But if you want to specifically say that something need to be 0, so you can say that in TCCR0A. I will AND it with the NOT function of COM0 A0, that we wanted to keep it 0. Right? So let me terminate this. Let me give this a space. Yeah. So this is equivalent to this, what we did. And that is, but this is a more recommended way because you are using the variables and it is compatible across multiple processors. So this is the TCCR0A. You need to also set the TCCR0B because it is a 2-word register. TCCR0B is equal to. So let us see what that is. One time if you do this, then it will be there as a template for you to do other applications. So here is the TCCR0B timer counter. There are few settings that we need to. So you see that waveform generation mode 02, this should be 0. So I will set this one as 0 and I will leave all this. And here you have CS00, CS01 and CS02. These are for deciding the PWM frequency, pre-scaling the clock. So let us see what we need to do for this. So this will remain 0, this will remain 0, this will remain 0. So and this is also 0. I will specifically make it 0, ensure that it is 0. And what should be these 3 bits, LS bits? So let us go to the table. So these are the clock select bits. 000, no clock source. 001, no pre-scaling. It is just divided by 1. 010, it's a divided by 8. 11 divided by 64. 100, like that, divided by 256, 1024, so on. So let us say, for example, now I'm going to use this. Divide by 64 clock pre-scaler. So which means that I will go to this register and do this following setting. 0, 1, 1. Then my TCCR0B would be set. So let us go back to the code and first let me define what this is as a comment so that you don't need to search when you are reading the code later on. So let me go back here just to see FOCOA. This is force output compare. This we are not going to use. FOCOB. Then these 4 bits. So let me write that down. Force output compare OA, force output compare OB, then reserved WGM02, and then CS02, CS01, CS00. These are the bit variables for clock select. And what is it that we have chosen? TCCR0B to be equal to binary. So we have this binary which is 0 0 0 0 0 0 1 1. And the recommended way, I could have used it in the binary fashion. The recommended way would be to use the bit variables. So let me TCCR0 B. So I will OR it with itself, okay, and set CS0 1. This is one thing that I'm going to set. Then or I will also set it because I want to give 1 1, right? 1 CS 0 0. Okay, and TCCR 0B. I will use and it with, I want to set the CS02 to 0. CS02 to 0. So this will set your clock prescaler. So actually I will indicate that PWM frequency can be set by adjusting this. So you can set the top value for there is OCROA. This is the output compare register. You can get the value of this by looking at the data sheet. So if you look at the data sheet, so in the data sheet, we go to the fast PWM mode. So in that section, you will see the PWM clock frequency given by the F clock IO by N. N is the prescaler value, in this case 64, because we have set CS00 and CS01 as 1 and 1, and 256. So this will give you the PWM clock frequency. And there are two compare register, OCROA and OCROB. You can use OCROA to set the top value of the counter. By top value meaning that when the count reaches the top value, it will reset. It will clear. So that like here. So when it reaches the top value, it will clear. When it reaches the top value, it will clear. So that is for update. So that value can be set. So if the top value is higher, then it will also affect the frequency. Okay, it will go and give you a larger PWM period and therefore lower frequency. If the top value is lower, then you can get a lower period and higher frequency. So the top value in conjunction with the scaling will give you the PWM frequency which you need to adjust it. So I'll set top value, I'll set it at 1.124, some value. I will just say set this to adjust the PWM frequency along with CS pre-scaling value. Then OCR0B, I will set it to 0 right now. This can actually be used as duty cycle. You can give a variable, assign it to a variable, and use this for duty cycle. And after that, let me set PB0 as PWM output pin. That is, OCOA is enabled and OCOB on PB1 is disconnected. So therefore, DDRB, data direction register, I will say to it that will enable the pull up of PB0. So after that, you have the while loop. So after doing all this initialization, it will go and settle in this while loop. It will continue doing this while loop till a timer overflow interrupt occurs, because timer is counting up, and then once it reaches OCR 0A, it will reset and you'll see an interrupt generated. And once that interrupt is generated, automatically it will go to this timer 0 overflow ISR routine. So here you can set some duty cycle value and use it for adjusting the value of the duty cycle of the PWM which occurs at PB0. So I'll say uint 8. I'll say some variable duty. I will say some value 100 for now. Okay. So this is the duty cycle. This should be between 0, which is 0%, and 255, which is 100%. And OCR 0B is uint 16 uint. So duty into OCR0A plus 1 by 256. Okay, you will have to match the brackets. See that the brackets are matched. Okay. So this will be a PWM occurring at port PB0. So it will go through the initialization, set it in this mode, then keep doing this while. When the timer 0 interrupt occurs, it will jump to the interrupt service routine. It will go in here, set duty is equal to 100, and the output compare is accordingly set, where if it is 255, you will have maximum top value, and if it is duty is 0, you will have a 0 value. And according to the value of OCR0B, the width of the pulse in the timer gets adjusted, because OCR output compare register value keeps changing dynamically every ISR. Here I have kept it as a fixed constant, but if it is coming from the output of a PI controller, then this will keep changing and pulse width modulation will happen. So let me save this. Let's see if it will compile. So if I go here, build. So if I go to the build and click on that, so you see that it is building and then success. So looks apparently that the code has compiled. You should execute it onto the AT Tiny 85 and use an oscilloscope, probe at PB0 pin 5, and on the oscilloscope see the value of the see the PWM waveform. You can make this duty cycle variable so that every time it goes to the ISR, it can keep incrementing and then decrementing. Then you will see the pulse width varying on the oscilloscope.